Okay, how you feeling about power series? Pretty powerful, right? And again, this next video is going to introduce something new. It's really just another example. We're not going to go through it fully in depth. More just introducing a topic and just letting you see again how we can use power series and what that's going to do, and just giving you the power. I need to stop saying that. Giving you the ability to use this tool and be familiar with this tool, because it's pretty strong. So let's look at another equation. Let's name this equation. Maybe someone's already named it. Let's look at something called Hermite's equation. Okay, and what this equation looks like is, and this equation arises very often in physics. This equation, maybe ask your physics professor about this. That would be interesting. I should ask your physics professor about this too. Minus 2t dy dt plus 2py equals 0. P is a parameter. Might be interested in how whether we have any qualitative differences in this solution as that parameter varies. Maybe there might be a bifurcation. Who knows? But yeah, P is just some parameter. And what do we have here? We have a second order linear differential equation. Unfortunately, we don't have constant coefficients. But yeah, all the terms are linear in terms of y. Right? Nothing weird's happening to this derivative. Right? Nothing's weird happening to the y. And yeah, so we're good to go. We haven't really talked about second order differential equations yet, but don't worry, we will. And the good news is you don't have to. Because what did we do with power series? We turned a differential equation into an algebra problem. It was a hard algebra problem, but it was just an algebra problem, and we're going to do the exact same thing here. So to do that, again, do I need you to know the ins and outs of Hermite's equation? Do I need you to know the ins and outs of all this stuff? No. What I want you to be paying attention to is specifically how do we approach and how do we use power series to look at these? So we're going to use the same power series as before. Again, the Maclaurin series, which is the Taylor series centered at 0. You don't need to know that too much. What you do need to know, right, is that this is how we can write a function as long as everything is nice enough. Infinite sum of monomials. A polynomial with essentially infinite degree. Infinite degree is not really a thing, but that's what we have. And of course, we're going to need the derivative too. And just like before, right, we're going to take the derivative the exact same way we took the derivative before. It's just going to be n times a sub n, t minus 1, just the power rule. Again, we're going to ignore whether we can take the derivative in this way, but we'll also need the second derivative, which is just taking the derivative again. So all of the stuff we did before, we're just going to do it again, right? We just get n times n minus 1 times all this. And now we just plug all this stuff in, we strap ourselves in, and we get an algebra problem. So what is this going to look like when we plug it all in? Well, I'll do some of the legwork for you. Again, you could pause the video, you could do this yourself. I could spend 30 minutes doing it myself and showing you, but the important thing is what's happening. So what's happening is that this is getting plugged in here. This is getting plugged in here, and this is getting plugged in here. And when we do that, we get this equation. We're going to get 2pa naught plus 2, a2 plus 2pa1 minus 2a1. Wait, actually, that might be a typo. I'll look into that later. Or you can catch it for extra credit if it is. Times 2p times a2 minus 4a2. All right, I don't think it's a typo. Plus 12a4 t squared plus ... equals 0. So you can see, right, we again see our polynomial. Because if our solution's a polynomial, right, then our derivatives are going to be polynomials. So a polynomial minus t times a polynomial plus another polynomial is still going to be a new polynomial. And we just collected like terms here. All right. So here's our constant term, here's our linear term, our quadratic term, and so on, right? Infinitely many terms, a bunch of stuff. We're going to do a bunch of algebra because, again, just like in the first video, this needs to be true for all t. Okay, it needs to be true for every t, which means that all the coefficients have to be 0. The only way this is true for all t is if every single coefficient is 0. So this equals 0, if this equals 0, if this equals 0, and so on. So when you solve that, when you work with that system of equations, right? Again, this needs to equal 0. This needs to equal 0. This needs to equal 0. And when you do that, you're going to get the following, which I have shamelessly stolen from the textbook because I did not want to write it down. Woohoo! All right, so this is what our solution is going to look like. It's just a little algebra, everyone. Just a little algebra problem. But here's what I want you to notice. There's two ways of writing the solution. The first is in kind of that standard form, right? A naught plus our linear term is just a1 times t. And now our quadratic term is where that parameter comes into play. And then we have more things. Look at the pattern here. Right? The cubic term has a p minus 1. The quartic term has a p minus 2 times p, which is really p minus 0, right? Here, this is also p minus 0. The fifth term has a p minus 3, p minus 1. You're noticing some sort of like double factorial behavior, right? So this is exactly what we have. There's a few ways of writing that. We're also noting alternating signs of in the terms of our polynomial. Lots of different things to analyze here. But this is a solution. Again, we could decide how many terms we want. Right? Whenever we're approximating with Taylor polynomials, and with these power series, we have infinitely many terms. We can get an approximation taking however many terms we wanted. In the last video, we said if you take 114 terms, which is a degree of 113, if you take 114 terms, you get a pretty good approximation. It's also a lot of terms. And we see something really interesting here, because for specific values of p, very interesting things happen. Specifically, let's move this up, right? If p equals 0, and a couple other things, like specifically a naught, this is still our initial condition, and a1 is actually our initial condition for the derivative. When we get into higher order differential equations, we'll have to have multiple initial conditions. An initial, like think about like modeling the acceleration of something. If you have position, acceleration, and velocity all involved, you're going to need to know the initial start and the initial velocity to track that position if acceleration's at play. Okay, so if p equals 0 and if our initial conditions are really nice, so if p equals 0 and a0 is equal to 1, and a1, which is the first derivative, essentially we have no initial velocity. If all this happens, we get something really nice. What does a giant thing become if all these things happen? We get 1 plus 0 minus, oh, p is 0. So this is 0 minus, minus, oh, a1 is 0, minus 0, plus another 0, p is 0, plus another 0, a1 is 0. We get a bunch of zeros. Y is just equal to 1. That's neat. And look what happens if p is equal to 1. What do we get? And again, the same initial conditions. Well, if p equals 1, you could follow the same line of logic. This is 0 plus 1. And then if p equals 1, we get minus t squared. And then p is 1, so this is 0. All right. And then we go over here. And I think we actually might actually need different initial conditions here. I didn't actually write this down. Because if we get over here, if if p equals 1. Yeah, so this one has, I think, maybe slightly different. There's some initial condition here. You can do some initial condition here, and you're going to get this as your solution. If p equals 2, there's, again, some initial condition that we can give. That's going to give a really, really nice answer because most things are going away. And actually, p equals 1. Sorry. I'm getting things a little flipped. Yeah, we switch our initial conditions to make this work. Depending on what our initial conditions are, we actually get a very simple polynomial for some of our solutions with the right values of the parameter and with the right values of our initial conditions. And these are called Hermite polynomials, which I'm not too familiar with myself, to be perfectly honest. So that's why I'm not really familiar with what initial conditions give you there. But again, this is just kind of a, hey, these are a thing. They might pop up. But the really important thing from this video that I want you to take away is we can look at a second order equation, Hermite's equation, which again will pop up in physics. And we can use these techniques of power series to still get an answer, right? Set this up. How does it equal 0? Well, it has to equal 0 if each coefficient of this polynomial is equal to 0. We could do a bunch of messy algebra. And again, I don't really care if you can do messy algebra right now. I want you to understand that you could do messy algebra to get an answer. And then here's a little bonus fun fact. You can read more about Hermite polynomials if you'd like. That's pretty much all this video is, all right? You don't need to be too familiar with Hermite's equation, but just see another example that, yeah, there's more stuff you can do with this. And that's it for Appendix A and Appendix B. I leave you. Oh, you can't see very much. It's a nice view of October. Anyway, have a good one. And when we come back, we will return with the start of Chapter 2. We'll talk about higher order differential equations and systems of differential equations. So that'll be Chapter 2. See you later. Bye-bye.